All right, let's get going. All right, welcome everybody to the February 5th, 2016 meeting of the Ottawa Centre RASC. I should say, I guess, a very happy Chinese New Year. And we've got a very exciting program today. We've got some new speakers. And I think there's one speaker in particular. We've got some, obviously, we have Simon Hanmer. Let's see if this is working. Oh, there we go. As you can see, we've got Dave Chisholm, Al Scott, Kelly Jordan, and observations possibly in the first half. We'll see how we're going for time. Kelly Jordan's presentation, I think you'll find very interesting. And then we have, of course, the break, followed by the third part of Simon Hanmer's Mars series. So, sorry. Okay, so I think I'd like to welcome 7 new members, including the Horula family, a family of 4, who've decided to join the Ottawa Centre. I'd like to welcome you on behalf of the Centre, and I hope you find the experience as rewarding as I have, and I think we should all welcome them. And for those who haven't picked them up yet, as you can see at the bottom, membership cards are available from Art Fraser. Okay, members in the news. This is a photograph of Comet Catalina, and this was broadcast on the CBC and was taken by our very own Paul Cloninger. So, well done, Paul. That is truly amazing. It's on a national scale. That's truly amazing. And here we have the great Gary Boyle, who was on Rogers discussing astronomy. Gary, what was the topic of discussion again?
Really, just about the planets in the morning sky.
Planets in the morning sky?
In the morning sky.
Okay, cool. All right. I unfortunately didn't see it, but how long was the clip, or how long was the discussion?
Only 7 minutes.
Okay. All right. But
Roman, can I wear your glasses instead?
No. Yeah, actually, you know what, Gary? Next time you're on, yes, I'll loan you. I'll give you a loan of my glasses. Okay. So thank you very much, Gary, for taking the time and talking with the people at Rogers and expanding astronomy and furthering the education of astronomy. Thank you very much. Okay. And this is from Sky News, and the picture on the right is from our very own Pierre Martin. So thank you very much, Pierre. I don't know if you're out there, if you're watching on the web. Thank you very much, and amazing that you managed to get this picture into Sky News. So well done. Oh, sorry, it's the whole article. Oh, I apologize. I thought it was just the photograph, but no, it's the whole article. Well done. That's impressive. All right. So, without further ado, Dave, if you want to come down and give us a brief for the Ottawa skies in February.
Great.
Okay. Good evening, folks. So here are the what to expect in the Ottawa skies for February. Hopefully not as many clouds as we've had recently. Full moon is going to be on February the 22nd. Tomorrow morning, set your clocks early. This is approximately 6:30 in the morning, this particular snapshot. But there's going to be a nice triangle between Mercury, Venus, and the waning moon. I was looking at the skies, and it's about 20% covered, so you might be able to see it. So Mercury, its greatest elongation from the sun is on February the 7th in the early morning. And you should be able to see Mercury early in the morning for most of the month. Maybe towards the end of the month it's going to be too light. It's rising between 6 and 6:15. Venus is visible early in the morning, rising at 5:42 to 5:51 at the end of the month. And Mars is visible in the early morning. Jupiter is visible all month. And so it's 8:31 in the evening and rising, and then at 6:25 towards the end of the month. So it should be great to be able to see that again. Saturn is visible early in the morning. Uranus is visible all month, as is Neptune is visible the first part of the month. The International Space Station. The best viewing date is February the 15th, where it rises to 70 degrees. All the times are on here. And here's a picture of its path across the sky. If you go to www.heavensabove.com, you can get all this particular information. Just make sure you set your local location correctly. Otherwise, the default is off the coast of Africa, and nothing works when you do that. And there's a little cartoon to finish it up. Thank you.
Thank you, Dave. So we have some active skies for February, and hopefully it will remain clear. But as you all know, Ottawa skies are not conducive to good viewing. I think I once read a statistics map that said Ottawa's 50 to 60% cloud cover. So unfortunately, we're working against the elements when it comes to good stargazing. All right, and so now we have Al Scott with 15-minute astronomy news and some very exciting new news.
Thank you, Roman. So, the news for today is all about Planet 9, or Planet 10, depending on whether you are a Tombaugh lover. So who here has heard about Planet 9? Okay. So what I'm going to tell you about is maybe explain a little bit about what we know about Planet 9, this new discovery of a planet in our solar system, what the evidence is, and maybe some background on how it got where we think it might be. So, first of all, who here thinks that we've actually seen Planet 9? Right. We haven't actually seen the planet. All we know is that there's been a preprint put out for people to look at and for scientists to review, showing some evidence that's suggestive of a planet. And this is the evidence here. This is the main bit of evidence. And what it is showing is they're clustering of orbits of Kuiper Belt objects. And these are more distant Kuiper Belt objects. The graphs here, you see the scale on the bottom is in astronomical units, or multiples of the Earth's sun distance on the x-axis. And on the y-axis, there's different things. On the left, we have perihelion longitude. In the middle is longitude of the ascending node. And on the right is argument of perihelion. And what that means is basically where the closest point to the sun is in terms of a longitudinal angle of the orbit, and where the object crosses the plane of the solar system, and then the argument of perihelion, which is on the right there, it basically shows clustering of these orbits in physical space. So what we see is that there's a lot of objects that we've found up to about 30 astronomical units. You can see there's quite a few objects, and they're nicely distributed in all different orbital parameters. But these distant objects, the more distant objects that we've been discovering, seem to cluster. And this is the evidence. What we would expect is that over time, if these objects have been here since the formation of the solar system, objects out here should drift around and have random orientations and random angles of perihelion. But what we see is there's these ones on stable orbits all have very similar planes of their orbits and the way they're oriented. And what the astronomers have calculated is that the probability of this distribution happening randomly, it's probably not a sampling issue, it's an actual real clustering. The probability of this happening randomly on its own is about 0.007%. So something is some gravitational influence is causing these things to cluster. And what the astronomers suggest is that there's a large planet out there which is resonating with these orbits and keeping them herded in these similar angles. So these are mainly objects with perihelia greater than 50 astronomical units. These are really outer solar system objects. So the perihelion, again, is the point closest to the sun. So 50 times the Earth-Sun distance is the closest these objects approach. A little bit of a background. Astronomers have been discovering several large objects out in the Kuiper Belt, trans-Neptunian objects they're called. Pluto, we've come to know, is the largest so far of a family of these icy worlds. Eris is another one, which is very close in size to Pluto. And the discovery of these other objects, very similar to Pluto in similar orbits, are the reason that astronomers decided that Pluto doesn't deserve special status as a planet. So, these are all relatively small objects. The object that the astronomers think is out there that is herding these smaller objects, and Sedna is one of the objects that is being herded, would have to be much bigger. Here's a view of the orbits of these trans-Neptunian objects that have been clustered, and the putative orbit of Planet 9, which kind of goes through the hole in the middle of them, as it were. The object would have a perihelion, or closest approach to the sun, of about 300 astronomical units. So it's way out there. And this would naturally explain the clustered perihelions of these dynamically puzzling orbits. The object must have at least 10 times Earth's mass to do this. So we're not talking about a small object here. We're talking about a potential a gas giant, like a Neptune or a Uranus. 2 to 4 times the diameter of the Earth. It would have to have a highly elongated orbit, perhaps averaging 700 astronomical units over the full ellipse. There's a wide variety of orbits that are possible to explain this because the data, we just don't have enough data to firm up exactly where it is. But the period of this putative planet could be 10,000 to 20,000 years. And because the orbit is so elongated, typically the objects move faster when they're closer to the sun and slower when they're farther out. So most of that 10,000 to 20,000 years is going to be a heck of a long ways away. And this is possibly why it may exist and we haven't yet seen it. So, what's the phase space to look at? This is a cartoon from XKCD, a graph of diameter versus distance from me of potential planets. And you can see the area that has not yet been explored by telescopes is over here. This is the Earth. These are the planets that we can see at night. This is about the extent of what our telescopes can see. Planet 9, we could probably see it with a telescope. It's likely going to be on the order of 22nd magnitude if it's out near its aphelion. So it'll be very difficult to see and very slow moving. Also, the orientation of the orbit suggests that the aphelion is going to be somewhere in the plane of the Milky Way, so it'll be a dense area as well. The history of planet searches for exoplanets is long, and I'll just give you a reminder. The planet Pluto was discovered first by gravitational oddities in the orbit of Uranus, back noticed in 1906, which sparked a search that ended in the discovery by Clyde Tombaugh of Pluto in 1930, or Percival Lowell as well. In the 1980s, a 10th planet was proposed based on irregular orbits of Neptune and Uranus, which was later disproved when they updated the mass of Neptune based on the Voyager flyby. In the 90s, there was a large planet proposed near the Oort cloud. The Oort cloud, of course, is a cloud of where the long-period comets are proposed to come from, and it also hasn't been observed directly, but we know that something is out there storing all these comet protocomets. So they proposed that there was a large planet out near the Oort cloud to explain the orbits of certain comets. A lot of searches have gone on with telescopes, infrared telescopes especially. NASA's Wide Field Infrared Survey Explorer ruled out quite a few of planets. You can see here, any planet in this size range was ruled out by the WISE survey because they would have been detected in the infrared. So nothing larger than Saturn is out there toward the Oort cloud, or they'd have seen it in the WISE survey. So something smaller than Saturn could still be out there potentially. Sedna was discovered in 2003, as I said, as a dwarf planet with an elliptical 11,400-year orbit between 76 and 937 astronomical units, 2.5 to 31 times the distance from the Sun to Neptune. Its discovery led to suggestions that it was an inner Oort cloud object. It may have been deflected by a passing star or a large unseen planet. But if such a planet existed, the orbits of other nearby objects would also be disturbed. In December of 2015, there was a hint of a large object discovered in the Atacama Large Submillimeter Array. So this is a very cold object which is emitting thermal radiation, not in the infrared but in the millimeter wave, so very cold. But it was very close to the star Alpha Centauri. And the likelihood that this is actually Planet X is relatively low because the ALMA field of view is very small, and it would be quite a coincidence if a needle in a haystack was found, looking the first place you look near a star. So people probably think that this detection by ALMA was probably a closer-in Kuiper Belt object, or maybe two different objects caught. There were two images seen, but probably could be two different objects, or maybe an oscillating source. Nobody's quite sure, but unlikely that that was the planet that we're looking for. A little bit of the theory about how the solar system formed and why we think it's possible there could be a planet out there. Currently, the most accepted models of the formation of the orbits of the current solar system are based on the evolution of orbits over time throughout the age of the solar system. We know that roughly what the distribution of mass had to be in the primordial solar nebula and what the distribution of planets could be. After the dissipation of the gas and dust of the primordial solar system disk, the four giant planets were originally expected to be found on near circular orbits. Now, much of this has been deduced through massive computer modeling of different gravitational scenarios that could potentially lead to the solar system that we're in now, starting from what we expect is the distribution of the initial matter. So what we see here are the orbits of the four giant planets that we know today, relatively evenly spaced, and then a disk of little icy planetesimals out further on, roughly about 35 Earth masses of crumbled rock and ice. And what happens is that, although this is a stable dynamical situation at first, what happens is that these things are moving around and encountering the outer planet. And in fact, what many of these simulations show is that as these little icy bodies interact with planets, they're pulled into the inner solar system. And what that happens over millions of years, it pushes the orbit of the outer planets outward. So it's changing the dynamical stability of the system. And as the outer planets move outward, scattering these things inward, the three outer planets will move outward. Jupiter will encounter these and throw them out of the solar system due to its intense gravity. So Jupiter actually moves inward while the other planets move outward. And eventually what happens is that Jupiter and Saturn start to get into a resonance scenario where one Jupiter year equals two Jupiter years equals one Saturn year. And this 2-to-1 resonance means that they start oscillating and building up eccentricity. They're no longer nice circles. And this eccentricity suddenly makes Saturn encounter the outer ice giants, and these things get pushed around by Saturn. And they start shooting off into the disk here. And in a very, very short cosmological time scale, they scatter all of these objects and throw them out of the inner solar system. And where they go, they end up in the Oort cloud or the Kuiper belt on very elongated orbits. And then after a time, the planets again stabilize in their current orbits. And what actually happens is that in a lot of these scenarios, the two outer planets actually switch position. And that's very interesting. Now, people have tried to model this in a smooth scenario. What actually happens here is this: when these planets encounter these disks and start throwing them everywhere, the inner solar system gets bombarded with junk. Meteors, comets, asteroids come shooting in, and this is what astronomers think caused the late heavy bombardment, which is what scarred up the moon and created all the big maria on the surface of the moon. This is the period of time, about 100 million years after the formation of the solar system, that we believe there was this intense bombardment phase. But if the orbit evolution is smooth, all the models seem to show that the eccentricity of the inner solar system planets are too high, higher than what we see now. The only way that they can get a really good match is by what they call the jumping Jupiter scenario. And this is a stepwise separation of Jupiter and Saturn's orbits due to gravitational encounters with one of the ice giants. So instead of a smooth evolution, you have this jump in Jupiter's orbit, which has a better chance of reproducing what we see today. Frequently, this scenario results in the ejection of an ice giant planet from the solar system or into the outer solar system. And it's just maybe an interesting coincidence, or maybe a piece of evidence for the existence of an ice giant in the outer solar system. It actually works better with the gravitational models if something was thrown out there, which maybe couldn't form out there because there's not enough matter out there in the primordial solar system nebula. So where does that leave us? Well, it leaves a lot of people with telescopes looking in certain areas of the sky, trying to discover another major planet. Just to give you an idea of the scale, here's a series of zooms of the solar system. The first one was showing the inner solar system that we're familiar with the asteroid belt. Here's Jupiter, and then we zoom it into the middle and we see the outer ice giants, Pluto, and the Kuiper belt, where we've observed several objects. And then we zoom that one more time, and here are these outer solar system objects orbiting in their clustered planes and the putative orbit of Planet 9. So you can see how much further away it is than even Pluto, which is up till now what we thought of as the farthest planet in our solar system, and the farthest minor planet, depending on who you are. So this is way out there. But we still have this Oort cloud proposed, which is kind of the furthest extent of objects from the primordial, that are still gravitationally bound to the sun from the primordial solar system. Astronomers really have only a vague sense of what lies beyond the Kuiper belt. This disk of comets was scattered, as I said, from the primordial solar system into the Oort cloud, a humongous reservoir of dormant comets. Planet 9, if it's real, may be out there. The evidence seems relatively strong. The future will certainly give us more evidence as we discover more of these distant objects, and the announcement of this potential modeling discovery will certainly spur more discoveries, and we should keep our ears turned and our telescopes on. Thank you.
Thanks. Thank you very much. Actually, Al, just before you go, just for a sense of scale, you said that Planet 9's purported closest approach would be 300 astronomical units. Mm-hmm. How far is Pluto from? Is it 35?
It's on the order of 35. Yeah.
So even at its closest, it's 9 or 10 times further away than Pluto.
Yeah.
That's impressive. All right, thank you very much, Al.
Thank you.
Okay. And now for something completely different. Et maintenant pour quelque chose complètement différent. This is got a tasty treat for you in store, from astronomy to gastronomy. See what I did there? De l'astronomie à gastronomie. This is a very interesting presentation. It's her first time presenting. Please make her feel welcome. Kelly Jordan and her conquête culinaire.
So hi there. For those of you who don't know me, my name's Kelly. I'm 16 years old, and I am in the International Baccalaureate program in 11th grade. So that means I'm a senior this year. And so during my last year, I've been working on an end-of-studies project called the Personal Project. What it is an individual project. Everyone has a different one, and it's always based on our interests and our passions and things like that. So I started working on this project in September, and I'm handing it in on February 10th. So I'm really in my final sprint right now. So what this project is, you may have guessed, is a cookbook that's based on astronomy. And I know that sounds weird, but about a year ago, I had to start thinking about what my project would be. And of course, I wanted it to be about astronomy because, like most of you, I'm very passionate about it. I was thinking maybe of drawing the moon, drawing the surface of the moon. I was told to consult Jim Thompson. Apparently he has really beautiful drawings. But then again, I have no drawing skills. So eventually I ran out of ideas. I put that aside, and I decided to turn to cooking, which is another interest of mine. And eventually I was just so confused, and I went to see my coordinator, and he told me, well, why don't you put them together? So what this is a dessert book, and it's full of pictures by you guys. I turned to the RASC because I wanted an original product with pictures that have never been seen before. I didn't want to just take some random pictures online and things like that. So what I did, I went on the RASC website. I had been to a few star parties, so I knew about it. I wrote to like the only email address I found, which was Chuck's. And when I came to the October meeting, he introduced me to a few astrophotographers. Most importantly, I met Bob Olson that day. Are you here, Bob? Okay, well, I met Bob on October 2nd, and I've been looking for him since October 3rd. He's been very, very helpful. He has made a huge contribution to this project. So I don't know if you know this, but the picture on the cover page is by Bob. It's a picture of the Pleiades. It's a beautiful picture. There's a beautiful story behind it. And there's a problem with the printing, so the photo credits for the front and back pictures didn't show up, so I have to be really precise about that. And those little asteroids, I suppose, that you see are called chocolate asteroids. They're drop cookies. And maybe you'll get a taste of them later on. So I'm just going to go through my book real quick, show you what I've got, and show you some fun facts. Unfortunately, the book is all in French, but if ever you want some translations or anything, you can come and see me at the break. So that's the first page. It's just this little introduction. The story behind this picture is a picture I took in September. And I was finishing my project on January 11th. I was rushing. I had no time to call anyone, so I just put a random picture I found on my computer. I know that doesn't sound very good, but the rest is more impressive. So this is my first recipe. These are called Sunny Cookies. What they are is just spice cookies. There's lots of cinnamon and nutmeg. The picture on the right is by Gary Boyle. And I know a lot of you guys have a lot of incredible pictures of the surface of the sun and things like that. I like this one because you can really see the warmth and the orange glow coming from it. All right, this one's really fun. This one is a hot chocolate recipe. First of all, I'd like to say the picture on the right is by Bob Olson. It's a beautiful picture of the Rosette Nebula. And what this recipe is hot chocolate, and you just froth milk and put it in, and it makes little clouds, and it all swirls around and makes really nebulas, but it's not as colorful. Okay, now this one was one of your ideas. I don't even know what their name was, but one of you members came up to me and said, you should make crater crepes. So I did. And I would like to mention this is my picture that I took in September. I'm proud of this one. So this is my very first observation report. I took this picture the evening of September 27th, the day of the supermoon eclipse. I took it with my 6-inch reflector telescope. I don't know what my camera is called because it's in the bottom of a pickup truck in Malaysia. So I took it that night, and as you can see, these are just crepes. You can do whatever you want with them. They're really fun. All right, so this was the original idea. This was the idea that started the whole project, and it's a vanilla pudding called the Milky Way, just because it's made with milk. So the picture on the right is by Joe Bonner, called Milky Way in the Andromeda Galaxy. I think he presented this one in November, and I just fell in love with it. I just had to go introduce myself and ask if I could use this picture because I just loved the colors in it. Now this picture you might recognize, we saw it just a few minutes ago. This is the chocolate asteroids that I told you about. And basically, I spoke to a lot of RASC members about having pictures of asteroids, but they all told me that it wasn't very easy to get them, that they all ended up looking like stars. So I decided instead to use this beautiful picture of the Perseids that was taken by Pierre Martin, and kind of make a little link between the asteroids and the shooting stars. So this picture was on the left, I believe, in his article earlier. This one's Lady Jupiter. There's no picture, but it'll come afterwards. This is a layered cake to kind of represent like the layers of colors in the planet. The picture on the right, once again, is by Bob Olson. And this one here, I believe, is by Gary Boyle. So here you can really see more of the lines, and you get a better idea of what the cake really looks like. So these are little star pies. They're really cute. They're so cute. These are pies that are made with carambola, which is the star fruit. And so the filling is made with it, and then you just put a little star on top. And this picture is also by Bob Olson. I told you he really helped me. And I really like the tones, the yellows and oranges in this. So it just matched perfectly, and I just love putting the colors together. And this is my last recipe. This is called the Eclipse, and what it is biscottis. And some people find this funny, but what it is cookies that are like dipped in chocolate. So I thought the link would be that it's kind of half hidden, kind of like an eclipse, kind of. So this picture here was also taken on September 27th. This is Paul Cloninger's photo. So if you have any questions, you can address yourself to him. This is the same story. I had no time, so I just grabbed an old picture. This is an acrylic I made in 2013. And I would just like to highlight that this book was entirely, well, not made by you, but you guys helped me so much. And this is just a page where I'm thanking people. For those of you who don't speak French, it just says thank you to all the members of the RAC who have helped me. And I really like to thank Bob Olson, Gary Boyle, Paul Cloninger, Pierre Martin, Eric Lemay, and Charles O'Dell. And also Joe Bonner. I'm sorry I forgot to write it. So that's pretty much it. I have one last photo, and before you yell at me, I know it's upside down. I flipped it upside down so that I could get like some writing on the bottom in the dark spot, and I thought that it really wouldn't matter, but obviously I still have a lot to learn. I was told, like, Kelly, your picture's upside down.
No, my picture's upside down.
I'm sorry.
In Australia, it would look like that.
Okay, fine. I'll just get an Australian accent.
No, but Roman was in Australia, so you can attest it. More or less.
So the reason I really wanted to show you guys this book is to say thank you, because this book would have never been what it is without you guys. And so, of course, my way of thanking you is bringing some cookies. So I have some cookies for you at the break. I'm going to be setting up at the table over there at the right of the stage. And what I have for you is chocolate chocolate asteroids, sunny cookies, and eclipse biscottis. So if you have any allergies, come tell me, and I've got something for everyone. And please come, say hi, introduce yourself. I would love to meet you, and you can take a look at the book. So thank you very much.
Kelly, before you go. That was just, I think, fantastic. I think we can all agree that that is, it's not just, it's such a creative idea, I think, to have done astronomy and cooking together. I don't think we've had a presentation like that before. But does anyone have any questions for Kelly? I can't see, so you'll just have to yell out. No, I guess not. Well, if you have any questions, Kelly, as she said, will be set up at the table at the break. So please feel free to introduce yourselves, as she said. Thank you very much.
But a comment.
Oh,
Yes.
sorry.
Lovely presentation. Thank you.
Thank you. Thank you very much.
Very well. And as I whispered to Simon, you have to follow that. All right, I think. Oh, apologies. What do you think, Chris? Observation reports? Sure. All right, let's do it. All right, observation reports. If you have an observation report, come on down. Who's first? Okay, there we go. Oscar, why am I looking up there? I've got it here. Oscar, Gordon, Webster, Jim, and Paul, please come on down.
Keep it light until they get down there.
Okay, great. Have you done this before? Yeah. Okay, yeah, and if you need the pointer, it's that one. Thanks. Go for it.
Turn all the lights off, please.
Alrighty, so it's, I guess I just hit the button, eh? Yep. There we go. So this is my image of M17, the Omega Nebula. It's also known as the Swan Nebula. This is one of the most well-known and observed deep sky objects in the summer skies. I took this image on the evening of June 20th. So this is an H2 region in the constellation Sagittarius, located some 5,000 to 6,000 light years away from Earth. It spans about 15 light years in diameter, and it's considered one of the brightest and most massive star-forming regions in our galaxy. Open cluster NGC 6618 is embedded in the nebulosity and causes the gases of the nebula to glow from the radiation of these hot young stars. This image is composed of 80 minutes worth of exposures taken at ISO 1600 using a Canon 60DA through an apochromatic refractor at f5. That's it. Thank you.
Okay, this is a sketch done of the occultation of Aldebaran, which was, about 2 weeks ago, a little over 2 weeks ago. And you can see Aldebaran is just about to go behind the moon. I did do photographs of it coming out from behind the moon, but trying to stack them and get the dynamic range to work so the star would show and the moon wouldn't be overexposed, I still haven't figured out. So, thanks.
Well, I suppose you're all disappointed because you can see this one. This one was taken last summer, as a matter of fact, because I cheated a bit. This is my DSLR on a C5 at the cottage. What I've been trying to show is point and shoot shots, but from last month's experience, we know how that turned out. Anyway, let's try one that I did try this month with my point and shoot in my backyard. Chris, here we go. ISO 200, 30 seconds at f3.3. It's Orion. And I've been using Orion as my test shot. But you can see at 30 seconds, it's a bit light. That was taken about 11 o'clock at night. Let's try the second one, Chris. 260 seconds. Doesn't seem to make a lot of difference. Chris? Okay, now this was taken this week. And I took it down. I had some shots at 800 ISO, but it didn't seem to make a lot of difference. But I tried this Tuesday night, and again it's Orion, just before the clouds came in. Chris? And, okay, this was last night. I went out at 11 o'clock to put the dog out, and it was all clouded over. So I went back out again at 11:30, and the sky was miraculously cleared. And as you can easily tell, that's Jupiter. Now, what I've learned in the last month is that, one, you shouldn't take astronomical pictures handheld. You shouldn't expect any results if you take pictures lasting longer than 20 seconds. You should rely on Chris to tell you when you send him garbage. And she's done a couple of times this week, as a matter of fact. But I keep trying. What I've also learned is that you need a steady tripod, something to put your camera on that you can be sure that you've got a nice, no star tracks or unnecessary movement. Now, it's been cloudy for the last 2 months, and I really haven't had a lot of chance to practice, but I have had a chance to do some other things. Chris? Hello, Chris? There. This is my tripod. I happen to have a pair of crutches in the basement, and I went out and bought another pair of crutches for $10. Then I went to the recycle store, and they had a nice piece of 3/4 inch plywood, 8 feet long, but only about 2 feet wide. But I bought it, and so I've probably got $20 tied up in that. I have a proper tripod head on it, which I found in my drawer, and I probably had it for about 5 or 6 years now. I don't show it there, but it's, now most tripods you look at they say, oh well, don't put more than 5 kilograms on it. But I know for a fact that you can put 215 pounds on it, and it won't fall down. So that was my experiment over January. I'm also looking at, I've got a photocopier lens that I had for years, and I've got that lined up so I can use that as a telescope. And finally, one more, Chris. I invested in a new telescope and another mount. What happens when you take pictures with point-and-shoot cameras, as you say, you know, I wish I could get a better view of that. So that was in Kijiji, and I got it for $45. It's a 4.5 lens on it. It's f5. I got it with the idea of redeeming myself with those moon shots, if we'd had the moon. But I'm waiting. And I'm prepared with my Home Depot stand. And in fact, that goes, it's a wonderful stand, and you can put it on top of a stool, which I can rotate. I take the stool out and I can rotate the pail on the stool. And you know, it's got a nice wide view, and that's, if the moon ever comes back out again, I'm ready. Thank you.
Home Depot, your neighborhood telescope store. I like that. Nice work, Jim. Hi, everybody. I've got a few shots for you tonight. I'll start off with this one. This is a time lapse that I shot a little while back. Essentially covers 3 hours and 25 minutes, just out my front door, basically. and I took 273 shots, 15 seconds with 30 seconds in between. So yeah, about 3.5 hours compressed into 18 seconds. So Chris, if you can roll that, it's a rather interesting play of shadows, and you can watch the stars setting, including Orion. Moon shadows, eh? I just found the shadow play of the trees on the snow to be quite interesting there, and when you see it fast like that, it's almost has kind of a bit of a creepy feel to it. So there you go, time lapse, easy to do. Just camera on tripod, 16mm lens, nothing fancy. Just take a whole pile of shots and stitch them together into an AVI movie, and there you go. Time lapse there, and you can see Orion setting there in the gap. All right. Okay, and the second one I have for you, let Chris roll that one up. Comet Catalina. So this was shot on January the 13th. Kind of my last good view of this comet. It's still quite visible with a camera, at least, up not far from Polaris. It is fading quickly because it is receding from the sun and moving farther away from the Earth as well. And so it's not nearly as bright as it was even just a few weeks ago. But in this particular shot, you can see the comet down below with its dust tail off to the right, and the ion tail pointing almost straight up. The bright star to the left is Alkaid, the last star in the handle of the Big Dipper. And up at the very top there, you can see Galaxy M51. Just in the view there. So the interesting thing with this shot is I took this with, thank you. I took this with a 135mm lens, so not a long telephoto lens, but I was experimenting with a new camera as well. I picked up recently a Canon 70D, which allows you to crank up the ISO to ridiculously high levels, including up to ISO 25,600. And so what this shot was actually just camera on tripod with a lens. There's no tracking involved here. I shot 20 images for this and stitched together like a 2-panel mosaic. But the exposures themselves, some of which were at 12,800, the others were at 25,600, with a fast lens, and that 135mm lens is at f2, so photographically it's quite fast. These were only 6-second exposures. So no tracking, nothing fancy here at all. Just a series of 6-second exposures, which I was then able to stack to reduce the noise from the high ISO levels, and resulted in that. So astrophotography made simple. So yeah, if you're at all interested in trying to see this or image this comet, if you're going to try to do that, try to get some skies in the next week or so while we have the moonless window, because it is dimming quickly. But it's been an interesting target over the last couple of months. All right, next one, please. So this is one. This is a project I'm working on, actually. So I'll give you a bit of background on this. 7,500 years ago, in our neck of the galaxy, a very violent event occurred. A large, massive star basically blew itself to pieces in a supernova 7,500 years ago. And for 6,500 years, the light of that explosion traveled through space until eventually it reached Earth 1,000 years ago. So in the year 1054 AD, this resulting supernova, this flash of the supernova, was seen and recorded, seen on Earth and recorded by astronomers in various different cultures as a bright daytime star. This star, this explosion, was so bright and so powerful that this was seen as a daytime star, in addition to the sun, a daytime star for several weeks. And then as it started to fade back, it was the brightest object in the night sky for months afterwards. So a very energetic event. It's a good thing it didn't happen a lot closer to us. You don't want to be anywhere within about 50 to 100 light years when one of these babies goes off, because that's just a bad hair day. You know, it's yeah, lots of radiation coming out of these things. it has been calculated by some that a supernova explosion within 50 light years of a planet could theoretically rip the atmosphere off a planet. So you really don't want that to happen. So fortunately, as I said, this object is actually about 7,500 light years from here, so we were at a good breathing distance from it. Anyway, this, as I said, it was recorded in cultures all over the world as a new star, and years later, 1,000 years later, with our fancy instruments, we can actually record the remnants of this, which is my next shot. So this is the Crab Nebula. This is a project I'm working on with a very sensitive camera. This is actually the light of the Crab Nebula just in hydrogen alpha. For those of you that aren't familiar with that, hydrogen alpha is a very common wavelength associated with nebulas in space. It is the energy released by hydrogen gas when an electron around a hydrogen atom falls from its third lowest energy state to its second lowest energy state, and it releases a pulse of red light at a very specific frequency. So I'm currently working on a project with this camera to record the Crab Nebula in various different bands of narrow wavelengths, including oxygen and sulfur. So basically, I want to produce an image using the Hubble palette of narrowband filters there. And as Jim pointed out, we haven't had a lot of sky in the last couple of months, so I've only gotten the hydrogen alpha data, but I thought that turned out fairly interesting, so I thought I'd share that with you tonight, because hydrogen alpha is, as I say, is very common, and not only is it an interesting picture, it gives you a sense of the dimensionality of this object. This object is now currently 1,000 years after we witnessed its explosion, is 12 light years across, and it's still expanding outwards at 1,000 kilometers a second. So the tendrils that you see, these red tendrils, are basically tendrils of hydrogen gas being energized by the neutron star pulsar, which is at the center of this nebula. When that supernova detonated, it blew itself to pieces, probably took out any planets that were orbiting around it, but left at its center a city-sized star called a neutron star, which is also a pulsar. So when you look at that with appropriate equipment, that pulsar is actually blinking at us 30 times a second as it's rotating. So you can imagine a star the size of the city of Ottawa rotating 30 times a second. Yeah, another object you don't want to get really close to. But yeah, very energetic object, and it's still it is the source of the light essentially that illuminates the Crab Nebula today. That pulsar puts out a lot of energy. It's absorbed by the gas, predominantly hydrogen, and then as that gas releases that energy, it releases a good portion of it in the red light of hydrogen alpha, which is what you're seeing there. So stay tuned. I'll try to get the rest of the narrowband stuff done before we lose that area. This is up in Taurus, and we'll see if I can get the full spectrum there. And then stay tuned. Come back in about 10 or 15 years, because I'll shoot this again. What we've seen with this nebula is that if you compare pictures taken 15 to 20 years ago with ones taken today, you can actually see the expansion of this cloud, because it's still receding, it's still moving out at 1,000 kilometers a second. So this nebula is actually growing. And so, the universe willing, I'll take another series of shots in about 15 years and see if I can replicate that motion there. I'll cross my fingers on that one. So.
Chris, would you have Paul, would you have an old picture of that object that we can compare to between now and what we saw, let's say, 50 years ago?
One that I've taken, or just?
Is it an old one?
You can probably download older pictures of this. In fact, that's what's been done. Pictures taken back in the 1990s compared to with pictures taken in the last few years show that expansion. There's a number of two-frame videos there where you can see the before and the after there. So you can, if you just ping it up on the net there, you'll actually find that comparison. But I just think it's cool that if I can do that myself and actually witness that event over a long duration, I think that's just a cool thing. So yeah, but a very three-dimensional structure. It's a really cool object. All right, so you'll have to forgive me for the next two slides. They're shameless self-promotion. But people have asked me about this. So I'm teaching my astrophotography course again at the School of Photographic Arts in April. Stu gave me a very good review of that. Thank you, Stu, and your check's in the mail. So yeah, in your astro notes of January there, thanks again for that review. and he summarizes what we do in the course. But essentially, for those of you that are interested in doing any kind of astroimaging that you've always wanted to get into or something like that, the course that I teach there is a 2-day workshop followed by a field session, which over the last few years I've been actually holding at my place. And so we get into astrophotography from the simplest levels, camera on tripod stuff, right up to high-end mounts in observatories with big telescopes. And the field session includes hands-on work, and we also get into the first stage of image processing. So people that have taken my course have asked me a number of times if it's possible to do a follow-up course, because the image processing really with astronomical images is pretty much a must for most types of astronomical images. You really got to work them a bit to get out the details in objects like, for instance, the Orion Nebula. So I put out a proposal to School of Photographic Arts for a new course. They accepted that and gave me a time slot. So this year, next slide please, Chris. I'm actually offering the follow-up, which is the capturing and processing of celestial images, where, again, it's a 2-day workshop at SPAO, which will focus almost exclusively on the actual image processing. So we'll get into a lot of the heavier duty stuff that's involved in processing celestial images there. So thought I'd just let you, for those people that have asked, just thought I'd let you know. Okay, you can just, if you're at all interested, just ping spao.ca and look under the part-time studies menu item there, and you'll find full descriptions of these courses. Thank you very much.
Thanks to everyone who submitted observations. So we're at the break. Before we go, so we've now got a fire sale price for the calendars. They're $10 each, and they're available. I believe they're up here at the table, kind of just off to my right. So today, I did remember to bring the tickets and the raffle box, so we will have a raffle. 10 minutes for a break, and don't forget to visit Kelly Jordan's table over here. So 10 minutes. All right, great. Just before we continue on with the rest of the program, I'll just explain how the door prize today is going to work. We've got the standard door prizes out front here, but this telescope has been very kindly donated to us by Gordon Webster, and this is going to be a special door prize. And the reason I say special is because you're kind of on the honor system. This is meant for someone who does not have a scope already. So this is to encourage give someone a leg up who's just starting out in astronomy, or who has been in astronomy for a while, just doesn't have a scope. So we're going to put all of you on your honor that if you don't have if you have a scope, and your number is called, because we're just going to use the same tickets, don't come up or just say, no, I've already got one, and we'll just keep going. So on with the rest of the program. I'll just put this aside. Oh, I guess this is the membership benefits page. I think we'll come back to this at the end of the meeting, but as you can see, there are quite a lot of benefits to being a member. All right, so this is part 3 in Simon Hanmer's Mars series. I like to refer to Simon as the Morgan Freeman of our center, that wonderful lilting voice he has. So Simon, please, part 3. Thank you very much.
Okay. Yeah, even I can do this. Good. As I pointed out in my last talk on erosional and depositional processes on Mars, I recently, that's to say actually over a year or so ago, discovered, if you will, a treasure trove of high-resolution images from the European Space Agency's Mars Express mission. And these have optical resolutions in the range of about 10 to 30 meters per pixel, Not only do these images contain astounding detail, they've also been rendered in oblique perspective, giving the viewer the firm impression of actually being there. Now, this European Space Agency image archive is so extensive, that it's required me a series of 3 talks to present just a selection of the very best that the European Space Agency has to offer, and I've divided them according to content. I've already talked to you about images related to Martian topography in general and processes associated with erosion and deposition on the Martian surface. So in this third talk, I want to present some of the amazing images the European Space Agency has to offer pertaining to volcanism and what I refer to as odd or unusual impact features on Mars. Just a word of warning, I noticed that the projection facilities are not quite in focus and they're not as sharp as they ideally should be and probably could be. So I'm hoping that even that some of the finest detail, that you'll still be able to see it. If not, then I know that it's visible on the computer screens, and so on the recording of this presentation, you'd be able to see the finest detail there. But let's see how we do. Can I go to the next slide, please, Chris? Thanks. Now, before we get to the images, I have to remind you of the main points of Martian geography using this digital elevation model, or DEM, which is derived from NASA. And it really brings out the principal topographic features of the Martian surface. You have the southern highlands down here in the yellows and the reds, the flat northern plains up here in the blues, the Tharsis Plateau with the Great Mariner Valley down here to its east, Syrtis Major, if you do actually manage to see Mars during a close approach and you see that the big dark blotch on it, that's Syrtis Major that you're looking at. Elysium Mons, volcanic center over here. And the Argyre and the Hellas impact basins. Let's go to the next slide. Thanks. And as I told you last time, Mars Express is a satellite on a polar orbit, and the images it takes are longer in the north-south direction. And that's unfortunate because computer screens are wider in the horizontal direction, which means that the European Space Agency has rotated all of their images so that north is to the right. And so I'll do the same thing in these presentations, but I will remind you. Now note the insert on the right up here. That's a location map derived from the NASA Mars digital elevation model with a flashing locator that'll just let you know in the slides to come where you are on Mars. So, okay. Let's go to Mars. First one, please, Chris. Now, our first port of call lies just northwest of the Hellas impact basin. And this is our first odd impact crater, but not our last. This is about 80 kilometers long by about 2 kilometers deep. And it's an odd crater for 2 reasons. First, it's clearly not circular in outline. We'll see why in just a moment. The European Space Agency suggests that this is the product of a very low angle impact, which brings us to the second oddity. If it's truly the result of a low angle impact, then the ejecta resulting from that impact is all thrown out sideways and symmetrically. There's the long axis of the impact feature, but here is the ejecta material on one side, and here is the ejecta material on the other. Now, that's not what you see in the standard model for low-angle impacts, as I'll discuss in a moment. Next one, please. Now, this is the digital elevation model for the same area, and it gives us some clues as to the origin of this odd crater. You can clearly make out, even on this, the topography related to the lateral ejecta thrown out symmetrically. But even more obvious are these 3 deep spots there in blue. And that suggests that the crater is the result of simultaneous multiple impacts, as the original impactor perhaps broke up just before actually hitting the Martian surface. Next one, please, Chris. Now, here's an oblique perspective image of our odd crater. You really can't see the 3 deep spots. They'd be in here. They're not very obvious. They're probably quite subtle in this photograph. But the lateral ejecta shows up very well. Here it is. It's streaked. And you can see it nicely here and out through here. The European Space Agency doesn't really have an explanation for this ejecta pattern, lateral and symmetrical. Low-angle impacts are supposed to project their ejecta directly downstream of the impactor's flight. Imagine it came in from here, then the ejecta should be out here. If it went the other way, the ejecta should be down there. Clearly, this is not the case here, and I don't have an explanation for you either. However, as we shall see, this is not an isolated case, certainly not on Mars. Next one, please. And this is just such a nice oblique perspective image of one end of that elongate impact crater that I simply had to include it. And I wonder if that hole right there is one of those blue spots which we saw in the digital elevation model. I think it is. Next one, please. So let's now skip west along the Martian equator to Orcus Patera. I do not know what Orcus means. I should have looked it up and I forgot to do so. It's a very odd structure, about halfway between the Tharsis Plateau and Elysium Mons. Now, this approximately north-south image, remember, north is to the right. It's elliptical. It's about 400 kilometers long. Note the 100-kilometer long scale bar. It's a pretty big feature. It does have a rim. It's got a rim. And that rim rises to about 2 kilometers high, suggesting that it is indeed an impact crater of some sort. Its shape would suggest that such an impact, if it happened, was oblique and low angle, and the shallow depth of the structure, about 500 meters, suggests that it was subsequently filled in with sediments or with volcanic lava. But the European Space Agency is not convinced. They even speculate on the possibility that Orcus Patera was originally a classical circular impact that was then compressed by tectonic forces to yield an elliptical shape. Now, I just don't buy that, because that's a lot of shortening and the surrounding terrain shows absolutely no evidence for this whatsoever. In other words, there should be mountains parallel to Orcus Patera, and they're simply not there. Next one, please. Now, the digital elevation model is pretty, but it's not very helpful in resolving the mystery of Orcus Patera. On the one hand, it confirms that there really is a significant raised rim all around the feature in these pinks and greys and beige colors here. On the other hand, it confirms that there's no visible evidence, and I emphasize visible, of any ejector blanket anywhere. Next one, please. This oblique perspective image gives us a visual confirmation of the raised rim and the absence of evidence for an ejector blanket. However, it also highlights the young age of whatever is filling the floor of Orcus Patera. See how smooth and undisturbed it is compared with the more disturbed area outside. In other words, there are very, very few impact features in there at all. Personally, I think this is indeed a product of low-angle impact, possibly by multiple impactors. But then, where's the ejector blanket? Next one, please. Moving on to Ares Vallis. Ares Vallis means the Valley of Mars, east of the Great Mariner Valley. And this is remarkable. This image is remarkable for the remarkable image has three parts. To the south, and that's on the left, remember, we see a terrain with small scattered bumps, some of which are flat-topped. You can see that here. See this one here, that one there? Those are clearly flat-topped. And some of these others are as well, if it were in better focus. And they appear to be the erosional remnants of a once more extensive plateau. To the north, on the right, we see a more extensive segment of Highland Plateau. That's all of this out here. And it's punched through by this rather large, about 30-kilometer impact crater, which is then itself breached and partially buried here on its southeastern side. But I want to draw your attention to the middle ground between these two terrains. That's this ground in here. Here we see a wide northwest-southeast oriented swath of smooth ground with a distinctive streaky appearance. These streaks here, and even finer streaks in through here. And this is evidence of the erosive power of rapidly flowing water, perhaps a series of flash floods that scoured the Martian surface within a very broad channel. The distinctive ridges of material preserved leeward of small relict hills, that's the material I mean in the lee. And there's an example of a small relict hill. There's another relict hill there with another lee of material. Suggests that the flash floods flowed from southeast towards the northwest. Now I think you can now see that it was these flash floods that likely breached the large crater here in that northern part of the image. But now take another look at this image. What's this dirt doing here in mid-field? Surely the European Space Agency cleaned its cameras before it actually sent the mission on its way. Next slide, please. And all is revealed in this oblique perspective image of the dirt. Good. It turns out to be a discrete patch of late impact craters. You can see them here. Very small in size and internally dark. In fact, there's a second discrete patch or cluster of such small impact craters there. And here is a diffuse streak of some dark dust linking the two crater clusters. These would appear to be distal ejecta, fallout from a relatively young impact far removed from this image's location, such that only the very smallest ejecta fragments made it this far, and in discrete flight groups at that. And judging by the dark color, the original far removed impact must have hit dark basalt lavas in the Martian surface. While we have this image, note how the general streakiness and the leeward ridges are very, very well resolved here in this image here. You can clearly see the resistant bedrock, if you will, and this is the material in the lee of that high ground. You can also see the margin of the flash flood channel in the background there. Next one, please. And looking now to the northeast across that breached crater, this oblique perspective image shows us two more of these clusters of small impact craters. There's one there, and there's another one out there. I think there's actually one here and one out there as well. And these are in addition to the clusters of impact craters we just looked at. Next one, please. So let's now turn our attention to volcanism and magmatism on Mars, and to geological features associated with them that we can see in the European Space Agency images. This digital elevation model of Alba Patera, literally a huge volcanic center located north of the Tharsis Plateau and north of its associated giant volcanoes, including Olympus Mons, which is down here. That would be the largest mountain, the largest volcano in the solar system. This image nicely illustrates the vast swarm of long, skinny rifts. That's these things in a big swarm. And these are associated with vertical sheets of basaltic magma, referred to as dikes, that were emplaced into the Martian crust while Alba Patera was erupting. Now, we're going to focus on detailed images at two locations in this swarm of long, skinny rifts. Phlegathon, indicated by PH, that's here, and Tractus, indicated by the TR, and they are both catenae. And what a catena is just a string of holes, as you'll see in a moment. Next one, please. So in this image from Phlegathon catena, we see an array of multiple, long, north-south oriented, remember, north is to the right, skinny rifts with their telltale geometry of systematic short offset segments. You can see the rift structure here quite clearly. These are also rifts, and if you look, you can see this systematic offset in orientation. You can also see it here in the big rift, the same systematic offset and misorientation. And that offset of segments, which have then linked to form the skinny rifts, that is something that geologists recognize as the signature of tectonic fractures. In fact, tectonic fractures which have moved sideways. Now, in the lower half of the image, we can see a chain of pits. And in fact, if you look carefully, you can see that the chain of pits itself has that same segmentation. There's one segment, and then here's the next segment. And they're offset with respect to the actual overall direction of the rifts or faults. And note the scale bar here so you get the size. Now, in fact, if you look closely at the main chain of pits, oh no, I've already said that, so getting beyond myself here. Next slide, please. There we go. Now, here's an oblique perspective image of the same area to give you a good idea of the topographic relief associated with these features. So this would be the rift, and here are the pits along it. Next one, please. Now, here's an example of the same phenomenon, but with different characteristics from Tractus catena. They're not small features here. Note the scale bar. Again, remember, north is to the right. So here we see a simpler array of 3 long north-south skinny rifts with their associated chains of pits, but this time they're crossed at a high angle by a subsidiary, smaller chains of pits. That's the ones I mean here. These are the subsidiary ones to these main ones. And again, the rifts and the pits and the rift. Next one, please. Now, both the skinny rifts and the chains are more spectacular when they're viewed in oblique perspective. And as I've told you before, these features are classical in volcanic terrains. Vertical fractures associated with tectonic forces form pathways for magma to rise toward the surface from the planetary interior. Where they attain the surface, we get volcanoes, such as Albufeira itself. Where they don't quite get to the surface, they cool as sheets of volcanic rock injected into the bedrock. And in cooling, they shrink. Or, while they're still liquid, they may drop back downward if the volcanic pressure decreases. Either way, this creates a void above the injected magma, and the surface materials collapse into a long, skinny hole that forms a long, skinny rift. And here's a beautiful example of one of these long, skinny rifts. Further collapse within the long, skinny rift, perhaps associated with the escape of volcanic gases associated with the injected magma, leads to the formation of chains of collapsed pits. And here you can clearly see the collapsed pits here. You can see them linking up, in fact, in that particular rift structure there. And here they are in this second rift structure. And that's about as good an explanation as you're going to get until we actually get down on the surface of Mars and check it out. Next one, please. Now, what about lava that does get to the Martian surface? What does it look like? Well, here's an image from Mardin Vallis, near the Highland Northern Plains boundary, just south of Elysium Mons. And what we're looking at here is a stack of 4 horizontal lava flows, one on top of the other. This is the top one here in brown. There's the second one below it. This is the third one below that, and then there's the fourth one right underneath everything. So this is going from high ground to lower ground. The uppermost lava flow lies to the west. Remember, north is to the right. And it's much darker than the 3 below it, so it's probably a different composition. In the northern part of the image, out here, you can see that the dark lava is actually covering the underlying lighter colored ones. Here they are, and the dark lava actually covers right across them. And all of the lava flows have wavy lobate margins. That's this here. See how they wave back and forth? They're lobate. And that's absolutely typical of the edges of lava flows in general. And the reason this would be sitting over the top and actually wrap over all of these is that that would be younger and these would be older. Now, in the middle of the image, here, is a very obvious skinny dike, a vertical sheet of basalt magma that cuts across the entire stack of lava and is therefore younger than the flows themselves. It may have been a feeder to even younger lava flows that may have been deposited on top of and therefore younger than the ones you see here, but they would since have been removed by erosion. And all of this is common observation in lava piles on Earth. There's nothing unusual here. Next slide, please. The oblique perspective image of the same area nicely emphasizes these volcanic features and shows that the dike is, there's the dike, is consistently darker than the lower 3 lava flows, 1, 2, 3. However, the description of this by the European Space Agency on their website is both confused and confusing. They describe a single lava flow, the dark one. They don't explain what the light-colored material is, but they refer to wrinkle ridges and the surface of the lava flow. Again, the idea that there's only one. The only things that resemble ridges in this image are these lobate edges here, which have some topography on them, of the 2 light-colored lava flows beneath the dark lava flow. Then they attribute the ridges to compression associated with the tectonic rise of the Tharsis Plateau, which would be way off to the east. I find this very strange. I find it very confusing. I prefer my interpretation, but then I would, wouldn't I? Next one, please.
So do we.
So let's now look at some features that actually look like volcanoes, starting with Tharsis Tholus, just east of the northernmost giant volcano on the Tharsis Plateau. Note that I've rotated this cropped image to place north at the top in this instance. Although an average-sized volcano by Martian standards, the base of Tharsis Tholus measures about 150 kilometers in the long direction, from here to about there. And that's about 3/4 of the distance from here to Montreal. The image clearly shows the extent of the slopes of the volcano and the 20-plus kilometer caldera, that's this thing here, on its summit. Now, a caldera forms either when the pressure of the rising magma quietly drops towards the end of a given pulse of eruption, or when the underlying gas or magma mix violently explodes into the atmosphere during the main eruption, and then takes the lid off the erupting volcano. Think Mount St. Helens in this context. In either case, a massive underground void forms into which the overlying lava deposits collapse, forming a caldera. And the word caldera actually comes from the same root as the word cauldron. Now, in addition to the caldera, we can see two radial cliffs. There's one, and here's the other one. That one's in shadow, and this one's illuminated. And they cut across the volcano's slopes. Now, these are the result of faulting within the volcanic cone, likely associated with the collapse and the formation of the caldera itself. Notice how the slopes of the volcano show evidence of impact cratering. Not a whole lot, but there's definitely evidence of impact cratering. Whereas the plain surrounding the volcano shows none whatsoever. So clearly, whatever material forms the plain is younger than the volcano that we see today, and the base of the volcano may in fact be much bigger than what we actually see here. But we're not done with this image yet. Look closely at the northeastern corner of the volcano. What do you see? I see short segments of what were originally long, skinny rifts. See that there? And there's actually another one right there. And as I've already shown you, these are likely collapse structures formed above vertical sheets of magma that didn't quite make it to the surface. But now look closer still, focusing on the northwestern quadrant of the volcano. Look at this, and this, actually. And here we see at least two linear features radiating out from the caldera itself, and each is decorated by a catena, a row of collapsed pits. And I think you can actually see that here, even on this projection. I think you can see it here. I think you can see it there on this projection. You certainly can on the computer screen. And these rifts and catena provide us with a nice confirmation of the genetic relationship between skinny rifts, collapse pits, and volcanism. But you've got to look for it. And luckily, these high-resolution images allow us to do just that. And next slide, please. Now, the digital elevation model for Tharsis Tholus confirms the topographic description I've just given you, but it also shows that the western part of the volcano is higher in the beige and the reds than both the caldera and the eastern slopes, which you see here in the yellow and the blue, thereby confirming the collapse model for the caldera formation. Next one, please. And this oblique perspective image derived from the digital elevation model serves to nicely emphasize the topographic dichotomy between the preserved high elevations and the collapsed half of the volcano, the high elevations and the collapsed half of the volcano. Next one, please. So staying in the same general vicinity, this image shows us two volcanic cones, Ceraunius Tholus, which is the larger of the two, note the scale bar by the way, and Uranius Tholus, which is the smaller. So let's focus here on Ceraunius Tholus, which is the larger one, with its summit caldera. That's this thing here. Now ignore the wispy white stuff that's here. It's not dirt on your glasses. Turns out that that's in the south, by the way. Those are clouds which were present on one satellite pass but absent on the others, on the other images which were used to make up this mosaic. Now I want you to notice two principal features on the slopes of this volcano. First, there's a very obvious channel that cascades down here on the northern slope, meanders its way down to the plain. And this channel was likely carved by a very runny lava flow that spilled out of the caldera, perhaps before the caldera collapsed, and flowed down the slope and straight into what is now an elliptical basin with a flat floor. And that just happened to be there, happened to be ready and in the right place, waiting on the surrounding plain. More on this in a minute. For the second feature, you have to look very closely at the southwest quadrant of the volcano. Remember, that's north, so there's the southwest quadrant. And you can see there a subtle linear feature radiating in a dead straight line from the caldera down to the surrounding plain. And if you look even closer, you'll see the linear is made of a chain of pits. I can just about detect them here. They're definitely clear on the computer screen. This is another example of Catena made of collapsed pits, and again, clearly associated with volcanism. Next one, please. Now, in the digital elevation model of these volcanoes, that confirms the elliptical feature. The elliptical feature on the north side of Stauroneus Solus really is a depression with a raised rim and a flat floor. And that's enough to make you really suspect that it really is, truly is, the product of a low-angle oblique impact. Now look again, and you can see the topographic expression of lateral ejecta symmetrically distributed around what would otherwise be interpreted as an oblique impact crater. Even with these two really clear examples, this one and the one from northwest of Hellas impact basin, I still have no coherent explanation for lateral impact ejecta like this, and especially not symmetrical lateral ejecta. Nor has anybody else, by the way. In fact, nobody seems to actually point it out. Next one, please. And this oblique perspective image of Stauroneus Solus nicely illustrates the coincidental, and I emphasize coincidental, relationship between the volcano, the plain surrounding it, the elliptical impact crater, and the lava river that emptied straight into it and contributed to filling the impact cavity. All of this is genetically coincident, but it likely occurred within the time span during which the volcano was active. Finally, next one, please. Let's now turn to the slopes of Pavonis Mons. That's the piggy in the middle of the three volcanoes that sit up on Tharsis Plateau. Downslope is to the southwest. Remember that north is to the right. And here we see an array of lava tubes in various states of collapse and up to about 60 plus kilometers in length. Note the scale bar, which is over there. If you look carefully, you can see that they range from open collapsed channels. That one's a pretty open channel here. That one's a nice open channel. That seem to originate at cobra head depressions. That's what I mean by a cobra head depression there. That's what they're actually referred to as formerly, cobra head depressions. That were likely originally small volcanic craters that have since been oversized. And they range from that to lines of collapsed pits. And you can just about make out the collapsed pit structure there. With this, there we go. This one here will show it. I think you can see the row of pits here, even on this particular projection. Well, they're actually all through, all the way through. You can see them here as well. Those lines of collapsed pits, of course, are the Catena we've been talking about. Now, I can clearly see the Catena in this image here, but I really want you to see them as well. So can we go to the next slide? Here is what we're talking about, the cobra heads, and there's the open channels. Here you can see the lines of collapsed pits. Oh, there we go. There's a nice line there. You can actually see how the collapsed pits have actually coalesced together to begin to form the full collapsed lava tube. There's another chain of collapsed pits up there. So, in other words, the chains of collapsed pits are real. Now this brings us to the end of this mini-series on what I think we can learn about Martian planetary geology from these superb high-resolution images from the European Space Agency's Mars Express mission archives. After all these diverse images on topography, erosion and deposition, volcanism, and unusual impact craters, what are my take-home messages for you tonight? Well, I stand by what I told you in my first talk in this mini-series, which I gave over a year ago. First, public space science agencies have a lot more for us to discover than they manage to tell us about. They're not hiding it. Their extensive images are in the public domain and they're readily available. All you have to do is go to their websites. They just don't do a very good job of telling us about it. Second, do go to the European Space Agency website and look at these images yourselves. The high resolution on your own computer screens is literally a wonder to behold. And thirdly, caveat emptor. Don't believe all you read on the NASA, JAXA, which would be the Japanese equivalent, or the European Space Agency websites when it comes to planetary geology. And so, with that note of caution, make the most of this excellent archive that the European Space Agency has placed in the public domain. Enjoy. And as always, thanks for listening.
Simon, thank you very much. I think I can speak for everyone that we enjoy your talks and find them, both entertaining and educating. To answer one of you, the question you put in your talk, Orcus Patera. Patera means pit. Orcus means either death or hell. So pit of hell or pit of death. Take your pick.
Welcome to hell, folks.
Yes. Thank you very much once again, Simon. So we've reached the end of today's center meeting. So we'll just go on. We have Estelle's pick of the month at the Stanmont Library. This is the Total Skywatchers Manual. Again, this is one of the benefits of membership. You can take a book out, I believe, for a month from the Stanmont Library. Oh, this is, once again, call for images for the 2017 RASC Observers Calendar. So, I mean, we've seen some amazing images tonight. If you have an image, I encourage you to submit the image to the RASC, to National, so that it can be included, or at least considered for inclusion in the 2017 calendar. This goes out all over the country, so it would be great exposure for anyone and for the center. I believe the deadline is the 28th of February, so you've got, how long? 23 days. So at the end of this month, your time runs out. But if we've seen some, for those who take those amazing images that we see on our observation reports, please submit. Benefits of membership, well, actually, this is the costs of membership. $75 for regular membership, $70 for a family, and $45 for a youth membership. I'll again say that I started as a youth member back in 1999. Some of the membership benefits, again, mentioned the Stanmont Library. There's also the Ted Bean Loan Library. So as a member, you can take out a telescope that's available for a month, and then you bring it back. But you can keep taking out telescopes as long as they're available. You also have access to the Fred Lossing Observatory, but I believe for those who are in the know, there is an extra charge, is there not? Yes, $35?
Key charge.
There's a key charge. Sorry, is it $35? Yeah, $35. There's a key charge so that you can have access to that.
No, but that's only to have access to the telescope in the warp room. Access
Oh.
to the site is no charge.
Oh, sorry, my apologies. Yes, that's correct. So access to the site is no charge. Access to the scope and the warm room is with a key charge of $35. You also get these with your membership. Included with your membership is the cost of these magazines and journals, and you get all of them. So you have Sky News, the Journal, the Observer's Handbook, which you get every year, and Astronauts, which is our newsletter. So club information, these are the individuals you would contact. Oops, sorry. Oh, actually, there we go. So our meetings are webcast, and I've been asked to also mention that RASC Kingston meetings are now also being live streamed. Eric, can you tell us what their schedule is like? When do they have their meetings?
Actually, it's Rick Wagner who does the
Oh,
streaming.
sorry.
I coached him on it, and we were still establishing it as a regular event, but it is available right now on our website, RASC Ottawa Live.
Okay, so it's available on our website. Rick, how often do the Kingston meetings?
Kingston meetings are on the second Thursday of the month.
Okay.
but they won't be streamed. We did it once last month, because Eric came down and did it for us. But further live streaming is on hold for the moment.
Okay.
But of course, everybody's welcome to come down to the meeting. It's only a 2-hour drive.
And where do they hold it?
It's at Ellis Hall, Queen's University.
Okay, so for those who may not have heard that, it's at meetings of the Kingston Center are at Ellis Hall at Queen's University the second Thursday of every month, but the live streaming is actually on hold for the time being. And this is our website where we have our meetings archived. You can download them or at least view them online. Christy, do you have any idea of the
85.
85. We'll go with 85. 85 people today at the meeting. Thank you very much, all of you, for coming, and thank you to all our speakers and observers, and to of course, our host, the Aviation and Space Museum. Again, I'll just remind you, the atrium is open, but the rest of the museum is closed, and of course, the toilets and other facilities are open. Post-meeting meeting is at Gracie's. You head down the Aviation Parkway and turn right, and it's within 100, maybe 150 meters on your right. Again, calendars for sale. $10. Are there any left? Nope, not anymore. So forget it. You missed your chance. Friday, 7:30 p.m. here, March 4th is our next meeting. And before you go, if we can have the house lights up, I'll start drawing for the door prize. So get your tickets out. Okay, and once again, I'll just remind everyone that we'll draw the special prize last. And again, it's meant for someone who doesn't have a telescope. So if you do have a telescope, we just, you're basically on the honor system to just say draw again. So. But first, we'll just draw the regular door prize, so I'll call out the numbers.
So let's say goodbye to everyone on the web.
All right. Bye, everyone on the web.